evening, everyone. Myself is Smita Roy, and today I'm going to present about my research topic based on electrochromic materials. So, before going to the serious later discussion, I would like to say that I'm not going to discuss much on the characterization part. Mainly, I'll focus and discuss about the application part. So let's start. So today I'm going to present the electrochromic materials property and all, and which started this optical memory to NIR Electrochromism, unique of electrochromic properties of coordination nanosheet with two different metal complex backbone. So before directly jumping to the discussion part, first I'll give a little bit about discussion about the background and motivation of the work. So the continuous increment of world's energy demand and consumption strongly depends on the traditional fossil fuels. Though there is a lot of research is going on renewable energy sources, but the share of the total energy consumption by renewable energy sources is very less. That's why it's very necessary and urgent to focus on some find an alternative which can reduces the fossil fuel consumption, which can reduce and optimize the fossil fuel energy consumption. Yes. So there is it is very besides the industry and transport, there is almost 40-50% energy has been used for building energy. So it is there is one data building energy building energy use data in 2020. I referred that almost 40% of the total building energy is used for space heating, space cooling, lighting, ventilation, etc. And another study also has revealed that the space cooling by air conditioning has grown to almost by 70% of the year in European countries. And sometimes during the summer times this AC dominates the peak power, the electric peak power during the summer time. So this kind of gives enormous energy, which is generally used, is only for our inability to control the solar radiation pass. The solar energy spectrum radiation on Earth shows that almost 44.7% visible solar radiation is responsible for solar daylight, whereas 48.7% contributes to the interior heating. So, the passage of this kind of solar radiation through any kind of transparent material like window causes the interior heating, and which leads to the unpleasant environment. Now, as most of the industrialized persons spend their 70 to 80% time on the indoor, so it's very necessary to maintain the indoor pleasant environment. At the same time, the visual contact should be very good. And to fulfill that, most of the people are using air conditioning and all. Now, air conditioning, we know it's continuous use of air conditioning is causes various harmful effect like greenhouse effect and all. At the same time, it causes serious health issues also, like skin allergies or there is skin allergies, and sometimes it causes nausea, dizzying, etc. So it's very necessary to reduce the air conditioning as much as possible. In this regard, it's very urgent to modify some window materials which can control the solar energy processes. At the same time, it should not hamper the visual contact. In this regard, there is a lot of window modified materials has been discovered, like phase transfer materials, thermochromic materials, aerosols, or organic liquid crystals, which would module the transmittance of the window by changing their transmittance. But one big problem is that this kind of material is very difficult to control the solar heat or light when there will be a certain change in climate. That's why the scientists have shifted their attention towards the electrochromic materials. Now, electrochromic materials are those which can change their transmittance, you can say, by simply triggering the voltage, which will causes some electrochemical reaction inside the material. The one big advantage of this kind of material is that we have no need to apply anything external stimuli like heat or light. Only just by applying small fraction of voltage, it can able to change their color. At the same time, it won't hamper the visual contrast between indoor and outdoor. So now come to the electrochromic materials. So as we know, so that's what we came to know, that electrochromic materials are those which can change their color by just applying a small fraction of voltage. And the color change is reversible. That means once we are applying the voltage, suppose they are changing their color to another step, again when reversing voltage, they are going back to the previous one. And that is a reversible color change. And due to this reversible color changing ability of this kind of material, they are highly applicable in different kind of sections. Like we know already, they are very highly applicable in smart home technology. At the same time, they can be used in information display devices, anti-glare rear view mirror, electronic papers, biosensor skins, military camouflage, etc. Now, there is lot of materials which can change their color when we apply the voltage, but not all the materials are applicable in commercially. So the materials only which is having very good optical contrast, very high coloration efficiency, a very high optical memory, cyclic stability, switching time, those are very good. Only those which kind of only the materials which is having very good these optical property, those kind of materials only can be acceptable as a electrochromic materials. Now I'll just tell you little about this parameter. Suppose cyclic stability. I told you the materials is changing the color when we applying the voltage. Now if we continuously change the voltage, okay, how this color or bleach state is stable, and how much time it is stable. That is, this is, if it is high stable, then obviously the material is acceptable. At the same time, switching time. Switching time means, suppose the compound is color. Now I applied the voltage and it's become colorless. How much fraction of time is needed? How much second or how much minute is needing to change the color? This is called switching time. Now, generally, according to the like work and previous report, we consider if it will change the 95% color in a something second, then okay, it is fine. The material is changing the color. So the switching time is like the time required to change the 95% of the color. If it is very fast, then the material is highly acceptable. At the third and important point is optical memory. What is optical memory? See, again we can see the picture here. I applied the voltage here, it changes the color here. Again, when you are going, if you are reversing back the voltage, it is going back to the normal position. Now I want to stay in the base state. So, okay, now then according to the definition of this electrochromic material, I have to constantly apply the voltage to stay in this particular state. Optical memory is that I don't want to apply the voltage. I want to stay in this particular base state, but in open circuit condition, we should not apply in any voltage. So how much time it will sustain in that particular state? This is called optical memory. So if you want to get the power efficient electrochromic device, the optical memory should be high. Because if optical memory will be high, then we have no need to apply the constant power, right? So optical memory should be high, and obviously color contrast. That means the transmitters and the bleaching and coloring state is there. So what is the color contrast between these? Those should be very high. So those are the some very important parameters which obviously has to follow by electrochromic material. Okay. Now come to the electrochromic our work. So there is lot of materials till now. A lot of research is going on electrochromic materials. Among them, some metal oxides like tungsten oxide, titanium oxide, vanadium oxide, then Prussian blue materials, and lot of organic molecules like hydrogen kind of molecule, triphenylamine based molecules. Lot of materials are already tested for electrochromism. Among those, organic metallic hybrid polymers is the modest one. So, what is organic metallic hybrid polymers? So, this obviously from the name you can understand this kind of polymer. So, it's a chelating polymer, you can say, where we are using some bidentate or tridentate chelating ligand. So, the chelating ligand may be bisphenolphthalein, maybe tartharidine, maybe bispiridine, whatever. So, there should be a chelating ligand, and it will chelate with the some metal ion. The metal ion generally belongs from transition metal family. So, so when we mix this, it's basically bidentate or tridentate. Basically bidentate or tridentate ligand with this kind of metal ions, they will form a polymer. Now, depending on the nature of the ligand, the polymer can be linear or hyperbranched. When we use this kind of linear ligand, bidentate linear ligand, they can form one-dimensional metallic supramolecular polymers. So we can use same metal ion, or we can use different metal ions. Okay. Now, when the ligand is linear, angular, not linear, angular. That means tridentate kind of thing. There is a possibility to form, and there is a chance to form the hyperbranched molecular structure. So for that we have to take a certain ratio of metal ion and certain ratio of ligand, and we just mix them, and they can form a hyperbranched polymer structure. Again, there are two kind of hyperbranched polymer. One would be like 2D co-ordination nanosheet, where the structure is it's a the growth of the polymer in 2 dimensional. Another is normal bulk polymerism method. We just mix those two ligand and metal and just heat them, and it will form like this. So this is the whole organic metallic hybrid polymer family. Now, the most benefit of this kind of material is they are strong, intense in color, generally because of the metal to ligand charge transfer spectra. Sometimes there would be a possibility of ligand to metal charge transfer, but most of the cases it's happened to the color generally it imparts the color generally because of metal to ligand charge transfer spectra. I just show here one example how intense the color is. Now come to the next one. What is our work? So I have shown here one example. It's also one kind of iron. This is the. Okay, sorry, I did not keep the example here. This is simple one iron plus bisphenol containing one-dimensional molecular polymer, which is normally it's intense violet in color. Now, when we apply the voltage, it changes the color. It changes its color and become transparent. And when it is reverting back, again the color is coming back. So, and the color change generally is due to the oxidation reduction of the iron to center. That I'll discuss in the later slides. So, what is we are saying? If you see the spectral design here, the green or red light is generally when the compound is in color state. So I'll just note down one point. When the peak is like this, like when the transmittance is very less, that means it's color. And when the transmittance is very high, that means light is completely passing, that is gray state. Okay, it's just opposite of absorption spectrum. So remember that. So we can see the lambda max is generally 581 nanometer, which fall in the visible region. Now, previous slide I showed that besides okay, sorry, one minute. In the previous slide I showed that besides the blocking of visibility, it's very necessary to block the NIR light also, because NIR lights are responsible for interior heating. Okay, but this kind of on metal supramolecular polymer only can block the visible light, not in the NIR region. And at the same time, another thing is that this kind of material shows very fast color switching, and the optical memory, the sustainability of the material in this particular bleach state is very less. So our aim to develop a optical memory device with fast switching time, at the same time to develop a visible to NIR modulated electrochromic device. That means the device which can block not only visible light, at the same time it should block the NIR light also. So now come to the our work. So in this regard, to fulfill this aim, first we have synthesized a simple tridentate non-conjugated tridentate organic ligand. Now, why I am saying non-conjugated? If you see this structure here, the conjugation is break. That's why I just mentioned it's a non-conjugated tridentate ligand. Now, we allow this ligand to undergo polymerization with iron 2 plus and cobalt 2 plus ions, but separately. First, and to get two different polymers, one is iron containing and another is cobalt containing coordination nameplate. So how I synthesize this? This is called coordination, preparation of coordination nanosheet at the interface. That means I am not applying, I am just mixing this ligand and this metal, but we are not applying any heat, nothing, just we are mixing the solution. First what we did, this TPY ligand, what is the ligand? That this is the chelating ligand. This is very highly soluble in DCM or acetyl whatever, but I have taken mixed with DCM, then and taken a beaker. Then on that we add the metal solution which is aqueous. So what you can see, there is a two immiscible layer has formed and the polymer form in between this layer, and they will form as a thin film. And you can see this color here, it is the pink color thing, which is iron. Oh, I did not mention here, sorry. This is generally for iron coordination nanosheet, and here you can see the cobalt coordination nanosheet. Okay. Now I'll one by one. I'll show you the electrochromic property of this iron coordination nanosheet. Then I'll jump to cobalt coordination nanosheet. So come to the general characterization. Already we all know the general characterization. I am not going to detail through this. So the polymer, already the coordination nanosheet is formed, and we have seen that the thickness what we got after keeping 2 days is 250 nanometers. Okay, and from XPS we have just calculated. Okay, iron 2 plus structure is present here. Now come to the electrochromism part. Oh, I will discuss this. Now, so before starting the electrochromism, it is necessary to know how we are preparing the device, how we are fabricating them, and then we will go to the electrochromism part. And what is the mechanism of that? That is very important to know. So, when we have prepared this kind of device, you can see by the image. So, how we are preparing it? So, for that, first we have to take this. This is glass where ITO is coated. ITO nanometer, ITO length, ITO thickness is about 100 nanometers. So we have cut this ITO slide first. We have taken this ITO glass. On that, we just deposited the film. What the film we are getting from the on the bilayer surface, that films we are depositing on that. Then so this is one electrode, and obviously this is conducting. ITO is conducting. So it will act as a one electrode. Now another electrode also we have taken, which is another ITO, normal ITO glass. There is no coating of any kind of material, just normal ITO glass. So that will act as another electrode. Now obviously to transfer the electron or something, there should be some electrolyte, like there should be some electrolyte which is jelly electrolyte. We are using jelly electrolyte where the cation is used as lithium plus and anion is perchloride ion. Now the main thing is that this kind of electrolytes should be ion conductor, not electron conductor. Okay. Now the thing is that when so this is the normal condition where where the fabrication device looks like that. Just simple ITO on that film, then gel, then another ITO, and those are sandwich kind of structure. Now, these kind of materials are intense in color. Why it is intense pink in color? As I told you, it's just iron 2 plus is there, so it's a D6 system, and the metal d orbital to ligand bister, the transition falls in the visible region, and that is called emulsified region, and is showing normal pink color. Now, when we apply the voltage across this device, okay, when we apply the voltage across this device, okay, near about the plus 3 voltage, what is happening here? So redox statement in the film is going on. So you can see from this signature arrow, so it's negative is indicating anode and this positive indicating cathode, and I connected this like this. When I am connecting to the negative side, that's when it acts as an anode, and we are applying some voltage of anode plus 3 voltage. This particular film where iron 2 plus center is there, those are getting oxidized and are forming iron 3 plus, and it's generating one electron. Once it's generating the electron, the extra electron is coming from the manufacturer going to the cathode, right? So when it's going to the cathode, the ions, those are getting separating out. So positive lithium ion is coming to the cathode part, and negative perfluoride is going to the anode part. And once the ion separation is happening, the film become colorless. Now why the film become colorless? Because when iron 2 plus become iron 3 plus, we know the DD splitting, T2G and EG. So suppose in this kind of here T2G is there, here EG is there. When iron 2 becomes iron 3, this T2G and EG gap separation would be high. So Fe3 plus T2G level would be down. Now from there to T2G, this T2G level to pi star transition, it won't fall in the visible region. It will go to the EV region. That's why we cannot see the color, and that's why the film become colorless. Now, when we are again applying the reverse voltage, what's happening? Again, this iron 2 plus center, iron 3 plus center, again it is taking back the electron, okay, and it's become color. And that's complete reversible process is happening here. And that's the main mechanism of, why this electrochromic material changes their color when we are applying the voltage. Okay. So now come to our electrochromism in our case. So already I have shown you how the solid state device structure would be like this. So the thing is, when again it's become color and colorless. Now see how could we understand this is some redox reaction is happening. That's we can understand from the cyclic voltammetry. When we are applying the voltage across this device, we have seen that almost at plus 3 voltage there is a hump. This hump is for generally oxidation of the iron 2 plus center, and that time only the film becomes colorless. When again we are reverting voltage at almost at -2, we can see the colored band. Okay, and when we kept the whole device in the UV chamber, in UV chamber we can see again at -2 voltage or at normal condition. See the spectrum here, transmittance is very less and lambda max is almost 556 nanometer, which is color state. When we are applying plus 3 voltage, it's become colorless. You can see here also this particular wavelength it's just decreased, and the intensity has decreased, and it's become this particular lambda max has gone almost. So that's it's breached, and emulsify is just disappeared. So this is how we are doing the electrochromism study. Now come to the parameters. So already we have seen the material is changing their color when you are applying the voltage and all. Now our basic study is how much time this continuous color changing and like color and discolor thing will stable for how much time. This is called electrochromic stability. Okay. And the second study would be how much time it will stay in this particular state when we stop applying the voltage. So that is the optical memory study. So just come to the next slide. Yeah. So now let's come to the AC parameter study. So it would be little difficult to understand the graphs. I'll explain here. So what we did already from the UV visible spectra, we have changed the particular at particular wavelength, almost 5.6 nanometer. There is a huge change in the emissivity region. Now we considered that particular wavelength region, and what we did, we just applied the certain voltage on that particular region. Okay, so we fixed all the parameters in instrument. So we can see, I told, when the transmittance is less, it's become color state. When the transmittance become high, it's become discolored. So from that plot you can see, as the time is going, so suppose here it's minus 2 voltage, it's colored up to certain time I applied. As I applied plus 3 up to 5 seconds, it is coming up again. Again I am applying minus 2 voltage for another 5 seconds. Again another 5 seconds plus 3 voltage, another 5 seconds minus 3 voltage, and this cycle I continue up to 5000 seconds. Okay, and we can see from that. So this is the this is the the whole cycle, and it is a zoom version of that. So for understanding, so this is the, we can see that, I'll just come to the parameters say. So we can see that TC based transmittance and color state. So that is this one, this particular transmittance value, and KV is transmittance at bleaching state. So what is the difference in between this? That will indicate the change in the optical contrast. Okay. And when we are constantly applying this voltage and it is going down, coming down like this, so after certain cycle, so I have run up to 500 cycle. What is the loss of that? So we can see it is slowly going down, but loss is only 2.91, which is very convenient compared to other reported compounds. Okay, so and we have calculated some coloration efficiency. I did not show it here how the calculation you can understand. So just you remember the coloration efficiency is 470, but normal compound, this kind of compound shows the coloration efficiency like what is the previously reported compound, they shows almost in the 300 to 350 centimeter square per coulomb. So but here we got our coloration efficiency is very high, which is 470.13, which is very good. And we can see the switching time. I told you from this time to this time. So this is bleach state, this is color state. So this is called coloring time. So how much time it is needed to change this color? So this is only 1.149 seconds. Again, it's when it is going back to the bleach state, it's taking only 2.49. So for the color, so from this parameter we can see optical contrast is very high, which is almost 53.19%. Again, high electrochromic stability up to 5,000, and more than that, I continued almost 10,000 seconds, but I have shown here only 5,000 seconds. Switching time is also very moderate. That means it will take very less time to change the particular color state, and coloration efficiency is also very good. So this material is highly applicable in commercial. It's highly applicable. Now my aim to check the electrochromic memory. That means how much time it can stay in the particular bleach state. Okay. So electrochromic optical memory is nothing but sustainability in the NIR oxidation state in open circuit condition, right? So this is our system. I did not show it here. Our system. So you see the spectrum here in the photos here. So when we apply the voltage, what we did, we first the compound was like this. We applied a voltage. So it's become colorless. Now the spectral region is like this, where the transmittance is very high. So it is the 0-minute data where we can see it's completely transparent. Now we just disconnected all the electric supply, and we just check the data. So after 5 minutes, 10 minutes, 15 minutes, we continue record the data. We have seen that slowly the transmittance is coming down. That means slowly it's coloring. Okay, and about 55 minute data we have seen almost 30% almost 80% color changes is done. Now that means here just we can see up to 50% up to 20, when it's come to 20 minutes, 25 minutes, only 50% color back is happening. But we did a comparative study with other reported compounds. Okay, so the same kind of compound already reported before. Where I told you, na, ours is non-conjugated, same kind of structure, but here it is conjugated structure, where we can see some phenyl kind of rings are there, okay? But there was no kind of phenyl ring, only some alkyl chain was there. When we have checked the electrochromic optical memory study of that, we can see only in 20 minutes the complete whole color back of that compound is happening in open circuit condition. Like 80% 0-minute data, and almost in 20 minutes is almost it's got back its color. Another comparative study we did, it's a normal one-dimensional polymer film. First also the same thing happened in 20 minutes, it's almost changed its complete color. So now what we did, we have taken the 3 data, and just when we compare it, we have seen that the image is not clear here, I guess, and we have seen that when other materials almost at 20 minutes they come back to their original state, our in 20 minutes is can return only 50% change of or 50% returning of the color is happening. That means we can say our system should almost 50% color retention, right? So that means it's having high electrochromic memory compared to other reported conjugated ligand famous ligand polymer ligand metal polymer. So now why our system is showing high optical memory compared to other reported system? So if you see, so we just anticipated some mechanism here, and just so here I have shown it's our system where there is no conjugation, and we have normally taken the one-dimensional polymer, and where it's all the conjugated polymers. Okay, now come to this point. Already we applied the voltage and it's become color. So all iron is there in class 3 oxidation state. So why it is, first of all, why it is when we are just disconnecting the voltage, why it is coming back to original color? Because there would be some diffused electron or diffused ions would be there in a gel. I told you that we are applying the gel because of the ion conductivity. There will be some trapped ions would be there, and at the same time on the electrode there would be excess electron, right? So when the film is there on the class 3 oxidation state or this state, now we disconnected the devices, but the excess electron which is staying on the classes on the items, this will go. This is called electrotransfer and electron hopping. So electron transfer as well as electron hopping from one center to another center through this conjugated structure is very high. So when the electron transfer is happening, automatically this iron 3 plus will reduce to iron 2 plus, and it will immediately form a color. It's come back to the original color. But what's happening in our case, though electron transfer is okay, but electron hopping is very slow from one center to another center, and this is because we are having some break it's a non-conjugated structure, so electron diffusion would be very less, and that is why our system is showing quite a high retention time compared to the previous conjugated polymeric structures. Okay, conjugated ligand polymeric structure. So we can conclude that our compound as it's showing a very good optical parameters like good switching time, good coloration efficiency. At the same time, it is showing very good high optical memory. Now this is the all about the iron containing cobalt nanosheet. So now come to the cobalt containing cobalt nanosheet, where the ligand framework is same, only we have changed the metal center from iron to cobalt. Okay. I did not show here the characterization, but it's as similar like how we showed there in iron containing compounds. So just come to directly electrochromism. So here instead of taking solid electrolyte, we have taken solvent electrolyte, where the solvent is nothing but lithium perchlorate in propylene carbonate and also tried in KCl water aqueous water. So it is showing there. So the compound, okay, the cobalt containing, that is normally bleached color, that is normally colorless. Why it is colorless? I'll show you. See, when this gap, okay, this you can see spectra first. This black color, okay, or normal ash cast, reddish color, that is showing our normal compound structure, our normal compound's color, which is colorless. and only the small hump is there near about that 453 nanometer and all. But there is no charge transfer spectra. Why? Because if you see this MOT kind of diagram, this is the ligand pi star, and this is the metal T2G, and this is the metal Eg. So this metal T2G Eg DD transition falls only 453 region, and we know DD transition is very weak. That's why we can see this kind of structure. But MLCT energy is very high. That's why from T2G to Eg transfer, T2G to pi star, it's not happening, and that is why there is no MLCT, and that is why we can see the normal weight structure, or you can say normal colorless structure. It's a normal condition. Now, when we apply negative voltage means we are reducing the compound. When we apply going to minus 0 to negative voltage, minus 1.4 voltage, we can see there is a small hump. Okay, and at the same time we can see when it is come to minus 1.4 voltage, this peak instantly came down, and it is showing some good lambda max in 3 different positions. Right, one is almost 419 centimeter, and another is 519 centimeter, and another is 1070 centimeter. So we can see, like, and at the same time, okay. So the thing is that here we can see the 3 lambda max, which is falls in the 2 in the visible range, even in 1 the NIR range. Now, as I discussed, our aim is to get a NIR electrochromic device, because the compound will block the NIR light. It will reduces the need of air conditioning, because interior heating would be less, because most of the solar radiation will be absorbed by this material, right? So, and what our aim was that we achieved here. Okay, our compound is showing some absorption not only in the visible range but in the NIR range also. And what is the mechanism here? Again, this is the cobalt 2. The MLCT is not happening. Already DD transition is happening. Now, as it is taking extra 1 electron, because it is reduction, and reduction cobalt 2 center is going to cobalt 1, that means it is taking 1 electron. So DD, the T2G gap would be less. Now the transition, all the transition from metal T2G to pi star, which is MLCT 1, that will fall in the NIR region. MLCT 1, that is falling up near about almost 419 nanometer, whereas DD transition, that will fall in the 519 nanometer, and another would be 1070, which is in the NIR region. So these 3 different lambda max we are getting from this structure. So that is the electrochromism. Again, when we are applying 0 voltage, it is again coming back to the original structure, because the cobalt 1 center again it is getting oxidized. So in electrochromism, nothing but it's just changing their redox state, and at the same time changing their MLCT or spectral region. Now again come to the so already we have seen the compound is very good, and it is showing NIR region feasible to NIR electrochromism. Now again the stability comes, at the same time the switching times and everything come. So those are the parameters. So first I did the same electrochromic study in aqueous solution. Okay, where the aqueous electrolyte, not solution, aqueous electrolyte, where KCl is the electrolyte, and the solvent is water. Okay, and that was 0.1 molar aqueous KCl solution. And we did we checked the transmitter state and 3 different wavelengths, because already from here we got 3 different wavelengths, right? So we have to check the electrochromic stability in this particular 3 wavelengths, and we have seen that up to 1500 seconds, that was very stable. But after that, the film was degrading. This is because as we are applying almost minus 1.6 voltage or minus 1.5 voltage, this is the region where water will split. Water will split, and hydrogen evaluation, this is called hydrogen evaluation reaction, will happen on that particular voltage. So as hydrogen evaluation is after certain time slow hydrogen evaluation reaction is going on, that film will come out from the the ITO substrate, and that's certain there will be a degrade of the film. Okay, so to avoid these things, because obviously water is there, that's why the water splitting reaction is happening. So what if we change the electrolyte? So next up, or next what we did, we have changed the electrolyte and we have used non-aqueous electrolyte, which is propylene carbonate. It's non-aqueous electrolyte. The electrolyte is lithium perchlorate. Okay, it's a lithium perchlorate. So when we check again the electrochromic spectra and all the spectral region, we have again in non-aqueous also we are getting 3 separate P, and again all are almost from falling from visible to NIR region, and where in almost all the region the delta T, like the color contrast is very high. And we checked the electrochromic stability, and we have seen okay up to 8,000 the data is, the compound is very stable. It is showing good data. So ultimately this is the parameters. Okay, we have in KCl water we have checked that it is stable up to 1,500 seconds. Beyond that, only for due to like what's this hydrogen evolution reaction, the compound is getting spoiled out. But in non-aqueous solution, it is up to 80,000 seconds. The compound is very stable. At the same time, it is including visible also. It is showing NIR modulation. That means it can block both the visible as well as NIR radiation also. And yeah, compared to other devices, the previous one here switching time is little high. This is only because propylene carbonate is viscous in nature, so the counter ion diffusion or like that ion diffusion I showed you, lithium or lithium ion or perchlorate ion, and the electron transfer will become a little less. The counter ion diffusion is little less because of the viscous nature. That's why it is taking quite high time to change the color. But okay, compared to other report, like lot of reported materials are there. Compared to that is completely moderate. So what we did ultimately finally what we did. So we have prepared one a non-conjugated tachyridine based tridentate ligand, and we allowed them to polymerize it with 2 different methods. One is with iron, which is known termed as iron coordination nanosheet, and this kind of compound it is showing good electrochromism. At the same time, it is showing high optical memory compared to other reported metal organic polymers. And in the second case, we have prepared a cobalt-containing method of co-ordination nanosheet, which is showing visible to NIR electrochromism. Okay, so and both the device, if you see here, as optical memory is high, so we have no need to apply constant voltage. So it would be a power efficient device. At the same time, if you see the cobalt one, as it is, we are getting the NIR. It can absorb the NIR light as well as visible light. So solar heating would be less. So the power need of air conditioning would be also very less. So both the materials are very power efficient device, and so that is how we can. Like okay, we have prepared the device, 2 separate device, power efficient device based on the same ligand structure, and that is how why this ligand is very novel compared to other reported ligands. Okay, so now come to the acknowledge part. So I sincerely acknowledge to my guide, mentor, Dr. Sanchit Chakraborty, and obviously my family who stayed there every time with me. BITS Learning Hyderabad campus for giving me this platform to continue my research work, and obviously DST Inspired Faculty Project for their instant and constant funding. And yeah, thank you very much. Any questions? Ma'am?
Yeah, I'm there,
Excuse me?
madam. Yes, Sudha, actually, I don't have any questions. I would like to congratulate your presentation. I
Okay.
have some questions, but I'll ask personally that questions.
Okay, no problem. Was it completely audible or something? There was any problem?
Yeah, no, there is no issue. It's
Okay.
very fine. fine presentation.
Okay, thank you. Okay, so I'm concluding this. Okay, I'm closing that.
Sure.
Okay.